There is an absolute, undisputed law of gravity that has dictated human architecture since the dawn of civilization. You build from the ground up, and you build vertically. The higher you go, the more the Earth wants to pull your structure down, and the more the wind wants to tear it apart. For over a century, the global standard for extreme engineering has been the towering vertical skyscraper. But deep within the dense, mist-shrouded urban jungle of Chongqing, China, a team of hyper-ambitious civil engineers and structural architects decided that conquering the vertical axis was no longer enough. They initiated a multi-billion-dollar industrial campaign to completely rewrite the fundamental laws of structural physics. They decided to build a massive, fully functional skyscraper completely sideways and suspend it 300 meters in the air, resting it precariously across the peaks of 4 independent vertical megatowers. This is not a simple pedestrian bridge or a hollow aesthetic arch. This is a colossal, 12,000-ton horizontal steel and glass behemoth known as the Crystal. It is a 300-meter-long floating city in the clouds, packing massive indoor gardens, commercial swimming pools, luxury infrastructure, and heavy mechanical systems into a suspended tube that hangs over a lethal, terrifying abyss. To understand how humanity achieved this impossible feat of levitating architecture, you must strip away the sleek glass exterior and look directly into the brutal, hyper-complex mechanical warfare that took place during its construction. This was a project where a single millimeter of miscalculation, a sudden gust of wind, or a microscopic flaw in a high-tensile steel cable could have resulted in a catastrophic structural collapse that would have leveled a city block. The geographical nightmare of this project began before a single piece of steel was even forged. Chongqing is arguably the most geographically hostile megacity on the planet. It is situated directly at the violent confluence of the mighty Yangtze and Jilin rivers. The city is essentially carved into deep, uneven mountainous valleys. Because of this unique topography, the region operates like a massive thermal engine, generating thick, suffocating river fog, unpredictable thermal updrafts, and violent wind shears that whip through the concrete canyons. Building standard vertical skyscrapers here is already an extreme structural challenge. But the Raffles City megaproject called for 8 massive towers clustered tightly together right on the riverbank, with 4 of those central towers designed to catch and support the colossal horizontal skyscraper. The foundation phase was an absolute industrial bloodbath. Engineers could not rely on standard concrete pouring. The sheer weight of the finished structure, millions of tons of concrete, steel, and human payload, threatened to literally sink the riverbank and cause a massive landslide into the Yangtze. To prevent the Earth from collapsing under the payload, heavy-duty pneumatic pile drivers and colossal rotary drilling rigs operated 24 hours a day under blinding construction lights, boring massive shafts straight through the unstable river mud and deep into the subterranean bedrock. They pumped thousands of gallons of high-pressure, fast-curing industrial concrete and thick steel rebar cages deep into the Earth's crust, effectively pinning the entire megastructure directly to the tectonic plate. The foundation was a masterpiece of subterranean anchoring, but it was merely the prologue to the true horror of the project. As the 4 central support towers began to rise into the sky, eventually topping out at 250 meters, the engineering team was forced to confront the impossible logistical paradox of the horizontal skyscraper. You cannot construct a 12,000-ton, 300-meter-long steel cylinder hovering in midair. Traditional tower cranes, even the most massive heavy-lift models on the planet, do not have the capacity or the leverage to hoist thousands of tons of structural steel sideways at an altitude of 80 stories. Furthermore, if they attempted to build it piece by piece in the sky, extending it outward from the towers, the unanchored steel framework would act like a massive sail. The violent, high-altitude wind shears funneling through the river valley would catch the exposed steel ribs, inducing violent torsional twisting that would instantly snap the temporary welds and send thousands of tons of raw iron raining down onto the densely populated city below. The sheer physics of wind resistance made high-altitude assembly a death sentence. To solve this impossible puzzle, the engineering directors made a radical, highly dangerous decision. They would not build the horizontal skyscraper in the sky. They would assemble the colossal beast entirely on the ground, resting directly on top of the project's retail podium. And then they would figure out a way to lift the entire, fully assembled structure straight up into the clouds. The ground assembly of the Crystal was a triumph of heavy industrial manufacturing. Thousands of high-altitude iron workers, structural welders, and heavy machinery operators swarmed the podium roof. They began welding massive, curved steel beams, some as thick as a bank vault door, into an intricate, interlocking skeletal matrix. The sparks from thousands of industrial welding torches illuminated the thick Chongqing fog night after night, creating an apocalyptic, cyberpunk atmosphere. As the structure grew, it began to resemble the skeleton of a massive, metallic leviathan stranded on a concrete shore. The horizontal skyscraper was built in 3 massive main segments, with the central segment alone weighing over 3,200 metric tons. It was clad in thousands of custom-engineered high-impact glass panels and reinforced aluminum louvers designed to flex under extreme pressure. But as the colossal horizontal tube neared completion on the ground, the psychological tension on the construction site reached a breaking point. The massive cylinder was sitting safely on the Earth, but its final destination was 300 meters straight up, resting exactly over the gaps between the 4 vertical towers. The gap between assembly and destination was a terrifying vertical void. To achieve the single most dangerous and heavy structural lift in architectural history, engineers had to abandon traditional cranes entirely and turn to a specialized, highly dangerous technology known as computerized hydraulic strand-jacking. This is not a system of gears and pulleys. This is pure, brute force fluid dynamics and high-tensile steel mechanics. High on the rooftops of the 4 towering skyscrapers, workers installed an array of massive, heavy-duty hydraulic lifting jacks. From these sky-high mechanical beasts, they lowered miles of thick, tightly braided, high-tensile steel cables, known as strands, straight down the sides of the towers to the ground. These heavy cables were then mechanically locked into colossal steel lifting lugs, welded directly onto the frame of the horizontal skyscraper. The basic concept was brutally simple. The hydraulic jacks on the roof would pull the steel cables upward, lifting the horizontal building off the ground. But the execution was an absolute mathematical nightmare. When you are lifting a structure that weighs thousands of tons, the payload must remain absolutely, perfectly level at all times. If the hydraulic jacks on one tower pulled even a fraction of an inch faster than the jacks on the other tower, the horizontal skyscraper would instantly tilt. Millions of pounds of gravitational force would suddenly shift to one side, violently snapping the high-tensile steel cables, ripping the lifting jacks right off the skyscraper roofs, and sending the 12,000-ton horizontal bullet crashing through the podium below, causing an earthquake-level catastrophic event. To prevent this apocalyptic scenario, human operators were stripped of direct control. The entire lifting operation was handed over to a massive centralized supercomputer. The computer was connected to a network of high-precision laser alignment sensors and digital strain gauges placed on every single inch of the lifting cables and the structural frame. When the countdown reached 0 and the great lift was initiated, there was no sudden jerk or massive movement. The massive hydraulic pumps engaged with a deafening, low-frequency hum, pumping high-pressure hydraulic fluid into the massive steel cylinders. Slowly, agonizingly, the cables tightened. The immense structural steel frame of the crystal groaned, popping and cracking as thousands of tons of dead weight were suddenly transferred from the solid earth to the braided steel tendons. And then, defying every logical instinct of the human brain, the colossal horizontal skyscraper detached from the ground and began to float upward into the mist. The ascent was a grueling, terrifying test of mechanical endurance. The massive structure moved upward at an agonizingly slow pace, often creeping at just a few millimeters per minute. The engineers in the computerized control bunker watched the telemetry data with breathless silence. Every single micro-adjustment in the hydraulic pressure was calculated and executed in real time by the algorithms. But as the 12,000-ton structure climbed higher into the vertical abyss, passing the 30-story mark, the 40-story mark, it left the wind shadow of the surrounding city and entered the high-altitude kill zone. Up here, the unpredictable river valley winds slammed into the massive flat side of the horizontal skyscraper. The structure was essentially a 12,000-ton pendulum suspended from thin steel wires. As the wind shear intensified, the massive bridge began to sway. Even a sway of a few inches was terrifying. The kinetic energy generated by a swaying building of that mass could easily bend the vertical support towers inward, compromising their structural integrity before the bridge even reached the top. To combat the wind, engineers had installed massive guide rails and heavy-duty Teflon-coated buffer wheels along the sides of the vertical towers. As the horizontal skyscraper crept upward, these heavy wheels rolled tightly against the sides of the vertical towers, locking the massive payload into a strict vertical track and preventing it from swinging out over the city. The lift took several agonizing, sleepless days. When the massive horizontal structure finally breached the cloud cover and arrived at the top of the vertical towers, 300 meters in the sky, the final and most terrifying engineering puzzle had to be solved. You cannot simply bolt a 300-meter rigid steel bridge directly to the top of 4 independent skyscrapers. High-altitude skyscrapers are not rigid. They are designed to be flexible. When a severe mountain storm hits Chongqing or when an earthquake strikes the region, the vertical towers are engineered to sway independently in the wind. If the horizontal skyscraper was rigidly bolted to all 4 towers, and 2 of the towers swayed to the left while the other 2 swayed to the right, the immense torsional strain would literally rip the horizontal building in half, tearing open the steel structure and shattering thousands of glass panels into a lethal rain over the city below. The structure had to be securely anchored to hold the weight, but it also had to be completely decoupled to allow the vertical towers to move freely. The solution was a masterpiece of extreme seismic engineering. Instead of rigid bolts, engineers installed a complex array of massive friction pendulum bearings and heavy-duty aerospace-grade seismic dampers between the tops of the towers and the base of the horizontal bridge. These colossal mechanical joints act like massive shock absorbers and sliding plates. When the vertical towers sway in the wind, the massive friction pendulum bearings allow the horizontal skyscraper to literally slide and glide over the top of the towers in a perfectly controlled motion. The seismic dampers swallow and dissipate the violent kinetic energy generated by earthquakes and wind shears, turning violent mechanical strain into harmless heat. The horizontal skyscraper is not just sitting on the towers, it is actively surfing on top of them. The entire interconnected megastructure behaves as a living, breathing kinetic matrix, constantly adjusting its center of gravity and shifting its massive weight to counter the forces of nature. When the final heavy steel locking pins were driven into the massive damper housings, a deafening cheer erupted from the exhausted ironworkers and engineers. The impossible had been achieved. Today, as night falls over the confluence of the Yangtze and Jilin rivers, the Raffles City megastructure transforms into a glowing cyberpunk beacon of absolute engineering dominance. The colossal horizontal skyscraper, illuminated by thousands of high-intensity neon LEDs, looks like a massive interstellar spacecraft docked permanently in the clouds above the city. Visitors walk through lush indoor gardens and swim in glass-bottomed pools suspended directly over a terrifying vertical drop, entirely oblivious to the extreme, brutal mechanical forces and heavy steel dampeners fighting a constant, silent war against gravity and wind just inches beneath their feet. China didn't just construct a building here, they completely redefined the spatial geometry of the modern metropolis. By successfully forging and lifting a massive skyscraper completely sideways into the abyss, they proved that human engineering has moved beyond simply surviving the hostile forces of nature. They have weaponized heavy industry, extreme computing, and high tensile steel to bend the very laws of physics to their absolute will, creating a dystopian, architectural marvel that stands as the undisputed king of the concrete jungle.
All 4 bearings loaded. The 4. The bearing.
Keep it coming, watch the alignment. Looks good from here, send it.
Verify these connection points against the schematic, please.
Confirmed. All readings match the parameters.
Easy, easy, keep it steady. Clear on this side, keep lowering. Bring it down 20. Easy now. Copy that, watching the west side clearance.
Check the input voltage on the gray modules. Reading stable power. Go ahead and secure it.